fatigue and factor properties of concrete mixtures with various water cement ratio presented by Stanislav.
Thank you very much, Mr. Chairman, for nice introduction. Okay, perfect. No, perfect. As you see here, it is fatigue and fracture properties of the concrete mixture with various cement ratios and various maximal size of aggregates. Which means that we try to catch two effects. One is the ratio of the water, and the second the size. The size is a maximal size, meaning that there is the aggregate from 0 up to 8 millimeters and 0 up to 16 millimeters. This contribution was prepared in slight cooperation of Institute of Physical Materials, Faculty of Civil Engineering, because it's about the concrete, then University of Oviedo and Faculty of Civil Engineering from Ostrava. Why we study this so important part of the civil engineering area? It is due to that all bridges which is prepared from concrete is usually fatigue loading. This means that the car is going through or some high-speed train or others fatigue load, and then that here could initiate some cracks, and from the cracks the cracks leads to failure of the construction. As we know it, the dependency of the load can be catched by SN curve, also known as a Weller curve. Aim of this contribution is quite easy. It is, as it's said in the title of the article, that we compare the fatigue test for 4 cars of concrete with a similar volume of cement but various volume of the water, and then we compare with one ratio 0.3 the two different sizes of the aggregates. Okay, maybe move it. For the other, this means that we for the evolution we use the basking or whole vehicle model. Here you can see some slight cyclic loading. As you see, our loading is not typical for sigma mass minus sigma mean. It means that we try to catch the amplitude, and for the bridges is typical. Ratio coefficient R is given sigma mean divided sigma max, and it is 0.1. Here you can see the typical description of the fatigue limit. There is the part of low cycle fatigue, and then high cycle fatigue. For some researchers, there is the fatigue limit, which is given by 1 times 10 power 7. But for concrete materials, it is given 2 times 10 power 6. It means only 2 million cycles. Okay. You can see here, as I discussed before about the stress ratio, the typical for rotation part of the engine is -1. Then for R in with the compression is this part, and then some of elements could be loaded by R 0, but in our case it's 0.1 because we suppose the load from the overweight, and we added some load from the car or train or this. Yeah? Okay. The SN curve is quite easily described by Weller. You can see here, this is the part for low cycle fatigue, and this is part for high cycle fatigue. It's quite easy. There is some broken specimen, and this is infinities unbroken specimens. While we studied, you see here, there is the low cycle fatigue. It means for structures subjected to earthquakes or structures subjected to storm. Then high cycle, it is good for bridges, wind power plants, airport plants, and super high cycle fatigue, it is mass rapid transit structures or sea structures. This is infinite number of the small waves. It is one node is nothing, but if we repeat many times, it damages the structure. Okay, two models we are applied, and one we selected as a vision for the results. We applied Pascual models. You can see here, which he described very well this regime of high cycle fatigue, yeah, and then described by this equation, where the B and A is material properties, yeah, and then fatigue limit is given in exact point. Then other model, it is Kohout-Vickert model. You can see that the base of the equation is similar like Pascual, but they catch very well both parts. It's low cycle and high cycle with this description. Okay, then you can see the last evolution here, and it's quite easy this model to apply. We use the software Excel and we avoid this data. Here you can see fatigue test, how we perform it. It is for concrete, it is so important to be 3-point bending test because it's typical bridge part, and it is tensile together with compression, and the bottom part is loaded by tensile. The grains propagate inside. For easy evolution of the position of vertical crochet, there is prepare some small, very short notch. It's A divided, with correct divided the typical dimension of the specimen 0.1. And then you see here the R ratio, as I explained before, and the frequency is very low. In our case, we use the frequency 10 Hz. There is some contribution by authors from Castilla-La Mancha. They show me that when we studied the fatigue load of the concrete-like materials, that up to 10 Hz it's independent, but if you use the high frequency, it's the material show like much better properties because there is no time to increase the crack before the notch. And then you see that for fatigue load, the limiter is 2 times 10 power 6 for this concrete materials. Okay, now I show you more interesting things. It is materials. We don't have the top secret like you, yeah, because we are a public research institution. There is, you can see the ratio of the water is 0.5, 0.4, 0.3. Then you see the aggregate maximum, it's 8 millimeters, and here you see the volume of this aggregate. Because if we give less water, we add more aggregates. You see it here, yeah? And then you can see there is the same ratio, 0.3, 0.3, and we give it crash aggregates here. Not to be added the crash aggregate 4 and 8 size of the dimension. Okay, now we have all 4 kinds of materials. It means that water and aggregates. Here you can see only for illustration. It is from the beam 80 times 80, and you see there is up to 8 millimeters, and then it's double size of aggregate. That you can see that the structure of the specimen inside. This is very good spread the stones, and that it's nothing that will be the stones on the bottom part, and it's very homogeneous distributed. Okay, here you can see some results. Okay, we obtained the results for volume density. This is the basic step. Then the compression strength, bending strength, module velocity, fracture toughness, fracture work. To obtain the information about the static or quasi-static properties. It is given by day, first day, of course, so important in bold, it is mean that 28 days, and then we tested in the how the properties change in time. That we tested after 3 months, and then after approximately 1 year. Okay, here it's better introduce this result. I selected the compressive strength, and you can see that from first day, 28 days, and then it still slowly increase or decrease the properties, and almost in time is very stabilized. Yeah, you see that for water cement ratio it is the 0.5, it is in the bottom part, and for 0.3 is upper part, and then almost independent on the side of the aggregate. See 8 millimeters and 16 millimeters. Yeah, it's almost on the same side. You see it here that for after 28 days it's 78 and 79. Yeah, it's almost the same because it's a mechanical test, compression, and from this the same we move it the young modules and etc. Okay, now so important information about the fatigue properties. We measured this SN curve, and you see immediately that as we suppose it that 0.3 it is the resistance it is in the bottom part, and when we give the less ratio of the water, the property increase. And index of dispersion is almost the same. It's nothing special that we some brittle material or something like this. Okay, now you can see the dependence of the size of the aggregate. Yeah, you see that the curve is not the same, but the points almost cover the similar curve. We could see that from 8 millimeters the better properties in this part, but if we move it to the resistance, you can see when this curve it's in this part better than the very similar, and you can see here that the triangle is upper part than this part of rectangular marks. Okay, let me conclude from this experimental research work. The following conclusion can be drawn. It's quite easy that the study found that the water cement ratio has a significant effect on the fracture mechanical and fatigue properties. And then this study didn't show any significant effect on the fatigue properties, especially on fatigue limit for different size of the aggregates. We only know that the scatter of the experimental result of all composite material is standard, and it's acceptable for this type of the practical use. And at the end, I would like to say thank you for your attention, and of course to the support for these two projects.
Thank you. So, any question from the floor?
Thank you very much for presentation. When you reduce the ratio water cement, so do you add something like adjuvants to mix it? Because you know at 0.3 it's really dry concrete mixture. So
yeah, okay, you mean that if we add it super plasticity area, okay,
didn't see
it's 1.5, 6 and it's increased. As I say that we replace the water with the
okay.
Thank you for the question.
I have another question. So what you show us before, it was the curve of strength of concrete at
compression.
Yes, compression. And after that, what you compare at the end, it was the flexural fatigue.
Yes, I wanted only to show it here, how it's changed the properties in time.
Yes.
And you know, the fatigue measurement, it takes time.
Yes.
And if we never start exactly in 28 days, because you see that still is some increase of the material properties.
Yes.
Then we make a decision to start after 3 months. And you see that after this time is not so changed, because if we measure the experimental program for the fatigue, if we it takes, for example, 2 or 3 months. It means that if we say, okay, we would like to start in 28 days, we have this curve for approximation to use, and then recalculating every points to 28 days.
Okay.
And we wanted to use this knowledge, not to recalculate it, that we all measurement for fatigue, as you say, in flexural load, we started after 3 months to avoid this change of the mechanical resistance. Yeah?
Thank you. I have another question, but we can discuss after.
Okay,
Thanks.
I'm prepared.
Thanks.
We have another
Thanks.
question.
Thanks for the presentation. Can you go to the table where you show the different properties you have measured? I think it was before.
Before, yeah. You mean fracture mechanical properties,
Yeah,
not
exactly.
fatigue, yeah?
There's
Okay.
also, okay, I understand why for 1 day they are missing, but what are the other things that are missing, like for?
Yeah, it is for 16 millimeters. We wanted to compare more this 8 millimeters, which is the standard, and the 16 millimeters was studied like we would like to expand our research part. Therefore, we didn't have enough specimens to prepare. That we make a decision. Okay, this is done. 28 days is quite easy. That we have to have it here, and then we should look it only after 1 year. How it changes these properties.
So you basically run out of specimens.
Yeah.
Okay.
Yeah, and of course here for 1 day, as you say, it's quite easy because after 1 day it's very difficult to measure the
More or
fracture
less,
toughness, more of fracture, only compression, and okay, volume is quite easy to measure. Yeah.
Okay, thanks. Just a question for me. Why did you choose only 8 and 16 as maximum diameter for your
because
and not 25 or 32, which are the most used in property technologies?
It is quite easy because our specimens, the standard specimens for fatigue which is used, it is 4 times 40 times 80, and it means if we wanted to study fatigue properties, we need at least 5 times, according to Karihalu recommendation, the rest of the ligament. This means that 16 times 5, it's if I say it, and it means that it's enough for the validation of the experimental measurement. Yeah, it's better of course for 8 millimeters, but 16 is on the edge of this experimental program.
Okay, thank you.